Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a pre-calculus lecture. I hope you enjoy it. This is chapter 1.5, which is analyzing graphs of functions. So first, let's start with a definition, right? And that is for a graph of a function. The graph of a function is the collection of ordered pairs in the form of x comma f of x, such that x is in the domain of f. All right. So what we're saying here is that, well, the graph is just the actual points. All right, all the coordinates all put together. All right. So let's do an example here. Use the graph of the function to find, well, we're going to find a few things. The first thing we're going to find is the domain of f. The next thing we're going to find is f of 0, f of 3, and f of -3. And lastly, we'll find the range of f. All right. So first, let me go ahead and draw what this function is going to look like. So there's my x and y axis, right? And let's say that this is my function, something like this. Right, where this is at -3, this is at -6, and this point we'll care about is at 3, and this is, we'll say it's at the height of 3 as well. All right, so let's go ahead and first look at the domain. All right, now to answer the first question, the domain, well, the domain is a set of all possible x values, right? If you look at this, well, this implies that it goes all the way to -infinity and +infinity. Well, the values here go to -infinity, but the x values go to +infinity. Similarly, over here, the y values go to -infinity, and the x values as well go to -infinity. But in here, when we're asking about the domain, we're saying, well, what are the values that we are allowed to plug in? Well, if you look at this, in here, there's a break, there's a hole, all right? So what we're going to do is we're going to say the domain is everything except that spot. So we're going to say, well, the domain is going to go from -infinity all the way up to -3, union from -3 to +infinity. And again, we're not including -3 because at the x value of -3, there's that hole. All right. Next question, part 2. So what is f of 0? Well, based on this graph, f of 0, here's 0, right? The x value is 0. What is the value of the function there? Well, it's at this height, so f of 0 is 3. What about f of 3? Well, f of 3, at this value, where the x value is 3, the function is at the height of -6. And what about f of -3? Well, f of -3 at this value is at this height, which is the same height over here. However, there's a hole there. So in here, because there's a hole, we would say it is undefined. and that's not how you spell undefined. Undefined. There we go. Better. All right. So that's those. Now, the last question here, part 3, was what is the range? Well, the range, it goes all the way. This again is implied that it's going all the way forever down to negative infinity. All right. So we're gonna start at negative infinity. But where are we going all the way up to? Well, it's going up in y values. It's stopping here. So that is the maximum y value. That's the maximum range. So it's going to stop at 3, and it includes that 3. All right. So it does include that. Now, you might be thinking that, well, because there's this hole here, shouldn't we also say that negative 6 is not part of the range? Well, that sounds like a convincing argument. However, on this side, negative 6 is part of the range. It is part of the possible outputs, all right? That's why we don't have to worry about this hole in this scenario. All right, so in there, that would be the range. Now, that's just reading the graph, right? Let's talk a little bit more about other aspects of a graph, of a function. So let's talk about the vertical line test. And this is what the vertical line test says. A set of points in a coordinate plane is the graph of y as a function of x if and only if no vertical line intersects the graph at more than one point. All right. A set of points in a coordinate plane is the graph of y as a function of x if and only if no vertical line intersects the graph at more than one point. What do we mean? So let's look at examples of things that are functions. All right. So, for example, in here, let's say I just had all these points. This is a function. All right. This is a function. It's a function because it passes the definition, right? I have a set of coordinate points, right? A set of points on the coordinate plane, and there's no vertical line that I can pass or that I can draw on here that would pass through more than one of those points. All right, so that's a function. Normally we don't look at functions like that, so let's look at a different example. Let's say, well, something like this. That's a function, right? Because there's no vertical line that can be drawn that would pass the graph at more than one point, all right? So what wouldn't be a function? All right, well, let's see. If I drew something like this, that would not be a function, all right? Because clearly, in here I've got a vertical line that passes the graph at more than one point, so this is not a function. All right. Something else that may not be a function would be something like this, a circle. All right. And there, also not a function. All right. And when we say that something's not a function, we mean it is not a function of x. All right. In general, we're implying that we're working with x as our independent variable. So we're saying that it's not a function of x. All right. Now, let's talk about something called the zeros of a function. right? So the zeros of a function. Well, the zeros of a function are the x values for which f of x is equal to 0, all right? The zeros of a function are the x values for which f of x is equal to 0. What that really is saying is the x-intercepts, all right? The x-intercepts are the zeros of a function. So if I asked, well, find the zeros of a function, I'm just saying find the x-intercepts. So in fact, let's do some examples of that. Find the zeros of each function, right? And by the way, before I actually do that, let's see why that would be, why this is a correct terminology to say. When we're saying the zeros of a function, we're saying where the y value is 0, all right? So here, the y value is 0. Here, the y value is 0. Right here, the y value is 0, and those are all x-intercepts. Okay, so now, let's find some zeros. So let's say I have f of x is equal to 2x squared plus 13x minus 24, all right? So let's see, what can we do here? We're going to find the zeros of the function, so the very first thing we need to do is, well, by definition, set it equal to 0, and then find the x values. So I've got 2x squared plus 13x minus 24 is equal to 0. All right. Now there's a couple of different ways that we can go about solving this. All right. So I'm going to do the AC method. All right. Essentially factor by grouping. And the AC method involves working with A and C. All right. So what do we do with those A and C's? Well, we say take 2, multiply with negative 24. So I'm multiplying A with C, and that gives me negative 48. The next thing I need is two values that multiply to negative 48, but add up to positive 13. Specifically positive 13, not just 13, positive 13. And well, those two values in this case would be 16 times negative 3, right? Because 16 times negative 3 is negative 48, and 16 plus negative 3 is 13, all right? So we need two numbers that multiply to this value up here, but add up to the value in the middle. Next thing we're going to do here is we're going to replace this 13. So what we're going to say is this becomes now 2x squared, and that 13, I'm going to write it as 16 minus 3. All right, so that 13x is 16x minus 3x. That's the same thing as saying 13, right? And then I'm going to copy the rest of that. The next thing I'm going to do is I'm going to group this. I'm going to group the first two and the last two. From the first two, I'm going to say, well, what can I factor out? I can factor out a 2x. And what are we left with? X plus 8. From the second two, what can I factor out? Well, I see they're both multiples of 3 and they're both negative, so I can take out a negative 3, and I'm left with an x plus 8, right? Negative 3 times positive 8 is negative 24. Set that equal to 0. At that point, you should notice that we have an x plus 8 in both of these, so we can factor out an x plus 8, and we're left with 2x minus 3 times x plus 8 is equal to 0. At that point, we say, well, we've got a product of two things equaling 0, so either the first thing, 2x minus 3 is equal to 0, or x plus 8 is equal to 0. From the first one, add 3 divided by 2, x is equal to 3 halves. From the second one, subtract 8, x is equal to negative 8. So those are my two zeros, all right? In other words, those are my two x-intercepts. At 3 halves and at negative 8. All right. Next one, so that was B. C. Let's say that I have g of x is equal to the square root of x minus 25, all right? And again, we're looking for the zeros of this function, okay? So what do? Well, we're going to set this function equal to 0. Square both sides to get rid of the square root. Add 25 to both sides. And there we go. That is our 0. X is equal to 25, right? Next one, D. Let's say that I have h of x being equal to x squared minus 2 over x minus 1, right? And again, we are looking for the zeros of this function. So what I'm going to do is I'm going to set this equal to 0. And what we've got here is a fraction equaling 0. Well, the only possible way for a fraction to equal 0 is if the numerator itself is equal to 0, all right? At that point, add 2 to both sides. So x squared is equal to 2. Solve for x. So we have to take the square root of both sides. But whenever we're taking square roots of an equation, we have to make sure we do a plus or minus, right? So x is equal to plus or minus 2. So, sorry, square root of 2. I forgot to take the square root. That should write that. Plus or minus square root of 2. There we go. All right, so we have to make sure that we do the plus or minus, but that you also take the square root. So in here, technically this means that we've got two values. X is either equal to the positive radical 2, or x is equal to the negative radical 2, right? But again, these are also the zeros of this function, okay? Now, let's do another example. E. So let's say we have f of x being equal to 6x squared plus 7x minus 3. All right, and again, the very first thing we want to do here is set this equal to 0, because we're looking for the zeros of this function. And once again, we're going to do the AC method. I take A and I take C and I multiply them together. So I have 6 times negative 3. Positive times a negative is negative. 6 times 3 is 18. And then I need two values that multiply to negative 18, but add up to positive 7. That's going to be positive 9 times negative 2. All right. So the next thing I do here is I'm going to write this as 6x squared, and realize here that I'm rewriting this 7x as plus 9x minus 2x. All right. Both of those together are just 7x. And then minus 3 is equal to 0. All right. At that point, group them. I'm going to group the first two together and the last two together. From the first two, I see that I can take out a 3x, and I'm left with a 2x plus 3. From the second two, I want to make sure that I'm left with a 2x plus 3. Well, even though 2 and 3 don't have any common factors, I can take out a negative 1, and I'm left with a 2x plus 3. At that point, I see 2x plus 3 in both of these, right? So I can factor that out, and I'm left with 3x minus 1 times 2x plus 3 is equal to 0, giving me that either 3x minus 1 is equal to 0, or 2x plus 3 is equal to 0. From the first equation, I get x equals 1/3. From the second, x is equal to negative 3/2. Now, I do want to mention something real quick here about the way that I factor this. I used 9 first and then negative 2 when I rewrote it here. There's absolutely no reason why you need to do it that way. You can rewrite this as 6x squared minus 2x plus 9x, and then a minus 3 is equal to 0. And notice there that this negative 2x plus 9x is still equal to just 7x as originally intended, right? That's what we wanted. Now I'm going to group these this way, these first two together and those last two together. From the first two, I see that I can take out a 2x, and I'm left with a 3x minus 1. From the second 2, I see that I can take out a 3, and again I'm left with a 3x minus 1. Alright, from there, I see that both of these have a 3x minus 1, so I can factor that out, and I'm left with 2x plus 3 times 3x minus 1 is equal to 0, which is equivalent to this line. Actually, not that line, this line, right? So from there, it ends up being the same exact work, all right? But I just wanted to show you that it didn't really matter the order in which we use this 9 and this -2, all right? All that matters is that that 9 and that -2 actually do multiply to that -18, and that they do add up to that +7. All right, so now let's talk about other aspects of a function. All right, so this is increasing and decreasing functions. So increasing slash decreasing functions. All right, so we're going to start with a definition. All right, so a function f is said to be increasing on an interval for any x sub 1 and x sub 2 in the interval if, well, the following is true. If x sub 1 being less than x sub 2 implies f of x sub 1, well, let me write this differently, implies f of x sub 1 is less than f of x sub 2. I don't actually want to write it that way. Let me just change the colors of these. I do want that less than to be like that. So f of x sub 1 is less than f of x sub 2. All right. So a function f is said to be increasing in that scenario. So let's see what this means. All right. So if I've got x sub 1 is less than x sub 2, here's x sub 1, here's x sub 2. Now we're saying that the function is going to be increasing on this interval for any x sub 1 and x sub 2 in the interval. If these two being less than each other implies that the function itself is smaller at x sub 1 than it is in x sub 2. So something like this. All right. So throughout this interval, this is increasing. Next definition. A function f is said to be decreasing on an interval if for any x sub 1 and x sub 2 in the interval if x sub 1 being less than x sub 2 implies f of x sub 1 is greater than f of x sub 2. All right. So what does that mean? Well, let's look at a diagram here. So this is going to be, well, here's x sub 1 being less than x sub 2. But now our f of x sub 1, the value of f at x sub 1, has to be greater than the value of f at x sub 2. So something like this. All right. That would be decreasing. So essentially, if from left to right, it looks like it's going up, it's increasing. If from left to right, it looks like it's going down, it's decreasing. All right. The last scenario that we'll talk about here is for a constant function. So a function f is said to be constant on an interval. Well, if f of x sub 1 being less than x sub 2 implies that f of x sub 1 is equal to f of x sub 2. So what does that look like? Well, here's x sub 1, and it is smaller than x sub 2. And here is my constant function. They're at the same height. All right, throughout the whole value, this height is at the same height as this one over here. All right, so those are the three definitions. And again, maybe I'll write them here. This one is constant. This one was decreasing. And the first one was increasing. All right. So those are the three scenarios there. Now, that's just some terminology to be able to talk about functions. Let's get more terminology to be able to talk about functions. So, relative maxima and minima. All right. So this is. So let's talk about the relative min and max. All right. Relative min and max. All right. So minimum, maximum is what we're talking about here. So now, a function value f of a, and perhaps I'll do that in blue. A function value f of a is called a relative min relative min of f when there exists an interval from x of 1 to x of 2 that contains a such that if x of 1 is less than all the x's, and that's less than x of 2, so all the x's within the interval. If that's true, if that implies that f of a is less than or equal to f of x. Alright, so for all the x's in this interval from x of 1 to x of 2, f of a, and perhaps I'll make that blue, f of a is less than all of the values in the function. All right. Now, similarly, we can say that a function value f of a is called a relative max of f when there exists an interval x of 1 to x of 2 that contains a, such that if x of 1 is less than x of 2, it implies that f of a is greater than or equal to f of x. So what are we saying there? All right, so let's look at an example here. And here I'm just going to draw some generic graph. All right. So let's say that we have a graph like that. Okay. And here we've got a couple of minimums. All right. And here is a minimum. Here is a minimum. And we've got a couple of maximums. Okay. Here is a max. Let me do it in red. Here is a max, and here is another max up here. All right, so essentially we're saying that the maximums are when you're looking at it very close to it, right, near it, this value is the biggest value around it. Very close to it, this value is the biggest value around it. All right, but it's throughout the whole interval, that's the biggest value. Similarly, for the minimums, throughout the whole interval, this is the smallest value. Throughout this whole interval, this is the smallest value. All right, but you need to have the interval being from both ends. All right. So essentially, another way of calling the max and mins is peaks and valleys. All right, that's another way that some people call it, but we're going to be calling maximums and minimums. All right. Now, those are just some that's just some nomenclature for being able to talk about graphs. Now let's talk about the average rate of change. All right. So the average rate of change. All right. So the average rate of change. So this is the definition. The average rate of change of a function from x of 1 to x of 2 is the slope of the secant line through x of 1, f of x of 1, and x of 2, f of x of 2. All right, so the slope of the secant line to the 2 points on a function is the average rate of change. What do I mean by that? So let's see. So I have here my coordinate axes, and then let's say that I have a function that looks something like this. All right, just something like that. And let's say that here is my first point, x of 1 comma f of x of 1, and I've got this other point up here, x of 2. Let me make more space. X of 2 comma f of x of 2. All right, and in here we're gonna have this line. All right. Well, all right, something like that. In here, well, what is the slope of this line? All right, the slope of this line would be, so maybe I'll do that in a different color. The slope, m, it would be given by f of x of 2 minus f of x of 1 over x of 2 minus x of 1. All right, that is the slope of that line. Let's move that over here. Oh, let's not move this. All right. Maybe I can't move it. That's fine. So that is the, in purple there, that is the slope, right? So that gives us the average value of a function. All right. Notice again that it's basically just the slope, right? I mean, it is the slope formula, y sub 2 minus y sub 1, but I'm writing them with values of f. Now, let's do some examples as to how to find the average rate of change. So, find the average rate of change of the function over the given interval. All right. So here we go. I think I'm in example F now. So let's say that I have f of x is equal to x squared plus 2x, and then we're going to give the interval from -3 to -2. All right. So we're going to figure out the average rate of change there. Now in here, we don't need to do the graph. All right. All we need here is, well, the slope of the secant line going through these points. So we know that the average rate of change is given by f of x of 2 minus f of x of 1 over x of 2 minus x of 1. Right? Always write down the formula whenever you need to use it. So in here, what does that mean? That means that I'm going to have f of -2 minus f of -3 over -2 minus -3. Let's see what we get. When we plug in -2, well, let's plug in -2 up here. So we have -2 squared plus 2 times -2. And then that minus plug in negative 3, so negative 3 squared plus 2 times negative 3. And all of this over, well, minus negative really means plus, so negative 2 plus 3. On the bottom, what does that give us? Negative 2 plus 3 is just 1. On the top, negative 2 squared is 4. 2 times negative 2 is negative 4. Minus negative 3 squared is positive 9. 2 times negative 3 is negative 6. All right. And at that point, what do we have? Well, we have 4 minus 4, that's 0, right? This is 0. And then minus 6, 9 minus 6, that's just 3. So we have 0 minus 3. 0 minus 3 is just negative 3. And since we have that over 1, our final answer there is just negative 3. All right. Next one. And again, here, we technically didn't find the slope. Maybe I'll rewrite this and I'll say that this is the average rate of change. Right, of this curve throughout that interval. Let's look at another one. So that was F. Let's look at G. Let's say that I had something like f of x is equal to 5x cubed minus 3x squared plus 2. And we're going to do this from negative 1 to positive 1, right? So let's see, our average rate of change. Well, that's going to be, again, f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. Always that, write down the formula, right? So what we have now is f of 1 minus f of negative 1 over 1 minus negative 1, right? This is sub 2, this is sub 1. And well, what does that give us? Let's see. Plug in f of 1. So we plug in 1, I have, well, 1 cubed is 1, 1 squared is 1, so I have 5 times 1, so that's 5 minus 3 plus 2. That's f of 1 minus, plug in negative 1. Well, negative 1 cubed is going to be negative 1. Negative 1 squared is going to be positive 1. So negative 1 times 5 is negative 5. Positive 1 times negative 3 is negative 3. And then we have this plus 2. All of this over 1 minus negative 1. 1 minus negative 1, that's 1 plus 1, right? Which gives us on the bottom, very simply, just 2. Now, let's see what we have. In this first part, 5 minus 3 is 2 plus 2 is 4. Minus negative 5 minus 3 is negative 8. Negative 8 plus 2 is negative 6. And then 4 minus negative 6, that really means plus, right? So 4 plus 6 is 10, and we have that over 2, which gives us 5. Next one. So that was G. H. Let's say that I had f of x being equal to 3x cubed minus 4x plus, let's just leave it as minus 4x. And we're going to do this from 0 to t, some value t. All right. So again, what we're going to start with is with our formula, f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. And this is really saying plug in t, plug in 0. So I have f of t minus f of 0 over t minus 0. And what's that going to give us? Well, f of t, just plug in t. So 3t cubed minus 4t minus plug in 0. So 0 cubed is 0 times 3 is 0. 0 times 4 is 0. 0 minus 0 is just 0. And on the bottom, I have t minus 0. That's just t. Notice on the top now, the only thing that we're left with is this parentheses, but they both have a t. So what I can do is factor out a t, and I'm left with 3t squared minus 4. All of this over t, giving me the final answer here of just 3t squared minus 4, right? Because these t's over there, they cancel each other out. All right. So that's the average rate of change. All right. And again, it is essentially just the slope formula. Now, let's talk about something called even and odd functions. All right. So even and odd functions. And first, we're going to start with some definitions. All right. Definitions of each of these. A function y equals f of x is even, all right, is even when for each x in the domain f of negative x equals f of x. In other words, what we're saying here is that whenever xy appears, the value x comma, negative x comma y also appears. All right, that's for an even function. Let me just copy and paste this. A function f of x, a function y equals f of x is odd when, well, let's change this. Margin erasing. There we go. When f of negative x is equal to negative f of x. So in other words, what we're saying here is if the point x comma y appears, then the point negative x comma negative y also appears. All right. So what are we talking about here? Let's look at the graphs. All right. So an example of an even function. So we're saying that the y value would appear for the negatives of each x value. All right. So what does that really mean? So something like this. All right. This right here would be an even function. All right. Because if I've got some value here, well, let's not start there. If I've got some value here, and this value is x comma y, then this other value over here, negative x comma y, also appears. All right. So that's for an even function. Now let's look at an example of an odd function. All right. So something like this. And in here, let's say we have this value right here. This value right here being x comma y, and whenever that appears, well, this other value over here, negative x comma negative y, also appears. And this again is an odd function. All right. Symmetrically speaking, graphically speaking, what you'll see here is that even functions are symmetric about the y-axis. All right. Whereas odd functions are symmetric about the origin. All right. Now, one thing I want to mention here, and I'll just briefly mention it. It is impossible for a function to be symmetric about the x-axis, right? And I want you to think about why that would be. Why would a function not be symmetric? Why would a function not be able to be symmetric about the x-axis? Well, let's think about it. Let's draw something that would be symmetric about the x-axis. So, for example, this. This is symmetric about the x-axis. But why is this not a function? Well, because it fails the vertical line test. All right, so since it fails a vertical line test, that is not a function, and in general, there is no function that is symmetric about the x-axis, no function of x. Now, so that was graphically how we can tell something is an odd or an even function. But how will we find it algebraically? All right. So determine whether the function is even, odd, or neither. All right. So determine whether the function is even, or neither. And let's see. We're going to start with f of x is equal to 5 minus 3x. And before we do it, let's go back to the definition for a second, because the definition itself already tells us what we need to do. All right. Notice that in both of these definitions are started with f of negative x. All right. It is even when f of negative x does something. It's odd when f of negative x does something else. All right. So we're going to start by figuring out what f of negative x is. All right. If we end up with our original f of x, then we know it's even. If we end up with the negative version of our original f of x, then we know it's odd. All right. So let's see. How will we do this? Well, I just said we started off by figuring out what f of negative x is doing. So what is f of negative x? Well, that would be 5 minus 3 times negative x, which is equal to 5 plus 3x. Notice that this is not the original function. This is not f of x. It's also not negative f of x. How come? Negative f of x would be the negative of 5 minus 3x, which would then be negative 5 plus 3x, which is not what we have here. So this is neither even nor odd. All right. It is neither even nor odd, because it's not the original function or the negative of it. Next one, J. Let's say that I had something like f of x is equal to x to the fourth minus x squared minus 1. All right. So in here, we're going to start off by saying, well, we need to figure out what f of negative x is doing. So f of negative x would be negative x to the fourth minus negative x to the second minus 1. A negative to an even power is positive, so I have x to the fourth minus a negative to an even power is again positive, so it's just x squared, and then minus 1. Notice that that is just my original function, f of x. So I have f of negative x equals f of x, and by definition, that is even. All right. Next one. That was J. K. Let's say I have f of x being equal to 2x cubed plus 3x. And again, we start off by figuring out what f of negative x is doing. And in this case, we have 2 times negative x cubed plus 3 times negative x. Negative x, or a negative value to a cubic, to a third power, to an odd value, an odd power, is negative. So I end up with negative 2x cubed. Positive 3 times negative x is negative 3x. Notice here that what I can do is, if I take out a negative value, or a negative 1, I end up with a negative of 2x cubed plus 3x, all right? And in here in parentheses, that's just my f of x, so I have the negative of f of x. So I started with f of negative x, and that showed me that I've got negative f of x, which tells me this is an odd function, all right? And what I want you to realize in these two examples, there's something here. Well, in here, this exponent here is a 1, right? Which makes it that value of 1. It's an odd value. This is an odd exponent. That's an odd exponent. Notice that all the exponents that appear were odd, and we end up with the function being odd. Similarly over here, there's an invisible x to the 0 here, and 0 is even, 2 is even, 4 is even. All right. So in here, we had nothing but even exponents on the variable, so therefore we get an even answer. Now that is coincidental, all right? You cannot use that in general because, well, look up here. This one we had an odd exponent and an even exponent, right? X to the 0. We just said that was an even exponent. So we had an odd exponent and an even exponent, and we found that that was neither. So you might be saying, well, okay, so if you have both even and odd exponents, then it's neither. Okay, so that rule, it applies for polynomials in general, and that works just fine with polynomials. However, we're not only going to be working with polynomials. So for example, I could have something like f of x being equal to x times the square root of 4 minus x squared. And the question here is this even, odd, or neither, right? Well, you can't just go by the exponents here because this is not a polynomial, all right? If it was a polynomial, we could, but this is not a polynomial. So we're going to say, well, what is f of negative x doing? Well, that would be negative x times the square root of 4 minus negative x squared. And what does that do? Well, this parentheses out here, they're not really doing anything. So I just have negative x times the square root of negative x quantity squared. That's going to give me positive, but with this minus on the outside, it stays negative. And notice here that what I really have here is this piece. It's just the original function. So I have negative f of x. So I had f of negative x equals negative f of x. This is an odd function, all right? This is an odd function. And we couldn't just rely on the exponents here, right? Next one. So let's do another one where you cannot just rely on the exponents. So let's say that I have f of x is equal to cube root of 4x squared, all right? And what is this going to give us? Well, let's figure out what happens when we plug in negative x, right? So it's going to give us the cube root of 4 times negative x quantity squared, which then in turn, well, the negative x quantity squared is positive x quantity squared. So I have the cube root of 4x squared. And notice that that's just my f of x. So I had f of negative x equals f of x. So that tells me that we're working with an even function, all right? So again, you cannot just look at the exponents. You actually have to do the algebra for it, okay? All right, so that is the end of 1.5. Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.